Hey everybody, welcome to my Tech Talk. I'm Shashank at AWS, and the topic for today is deep learning on AWS made simple. So let's say you're a developer or data scientist working with your deep learning projects, and one of the common questions we get is, how do you get started with deep learning on AWS? There's obviously a lot of different considerations with how do you set up your development environment, what kind of compute do you have access to, and how do you use them? How do you collaborate? What kind of storage options are there? How do you scale? And if you need to scale, how do you perform cost optimizations? How do you host your models? And so many other questions that we often answer because you, as a practitioner of deep learning, are more concerned with training your models and getting results. This talk is not about educating you on how deep learning works, but it is about how to simplify your deep learning projects on AWS. So with that, let's take a look at our graphical agenda here. So there are many different ways to set up your deep learning workflows on AWS. On the far left here, you see the simplest setup, which is you with your laptop or a workstation where you're working on prototyping and testing your models. Fair enough. But at some point in time, you're going to need more compute. You're going to need more storage. You're going to need to scale. And let's take a look at, after that, let's take a look at a very simplistic setup where you still continue to use your laptop, but use compute resources on AWS. And then we'll take a look at a free option to do this, a completely managed option to do this, and a completely DIY option to do this. Okay, few different choices for you. The cloud is all about choices, so you can set up your development experience the way you want it, get access to the right frameworks, get access to the right infrastructure. And again, at some point, you may want to scale your deep learning workflows. And there are a couple of reasons why you want to scale. You may want to scale to run more experiments parallelly to find out which is the best approach. Or you may want to speed up your training by distributing training on your cluster. And oftentimes, this is a challenging aspect for a deep learning practitioner who is not an expert on infrastructure. And we'll take a look at how you can do this on AWS. And finally, the whole objective of training a model is to deploy it and consume it for your customers to consume it, and which is where model hosting comes into picture. And as we go through this journey, we'll take a look at the developer experience. How does your IDE look like? How do you work on your projects on AWS? How do you get access to optimized frameworks? And what are the infrastructure considerations? And we'll take a look at cost, performance, and ease of use as we go through these workflows. Sound good? So let's dive deep. We'll start by taking a look at a simple but a great and effective workflow. Now, if you're new to AWS, then you know that you can get access to compute resources on AWS. Specifically, Amazon EC2 gives you access to compute resources. Now, if you're already an AWS expert, you also know that you can get access to EC2 to get working with your projects. And as a deep learning practitioner, you really need three key ingredients. First, you need access to compute. So you need access to GPUs and CPUs, and there are a number of different GPU and CPU instances, and we'll talk about. You need access to storage because this is where your data set lives, and this is also where you'll store your metadata and your models and such. And finally, you need access to software. This is your machine learning frameworks, deep learning frameworks like TensorFlow, PyTorch, and others that you're familiar with, but optimized for the compute environment that you're using. And we'll talk about that a little more. And of course, you need a development environment because that is how you'll interact with the infrastructure. Okay, so one of the advantages of a simple setup like this is that it mimics or mirrors your existing laptop compute setup. Now let's take a look at what this looks like very quickly. Okay, so one of the first things you will do in order to set this up is head on to the EC2 console page. And when you click on EC2 instances here, you can launch an instance very quickly and easily. One of the first things you'll do when you click this is take a look at variety of AMIs that are available to you, and an AMI is an Amazon machine image, and there are these machine images that are optimized for deep learning. For example, deep learning for PyTorch and deep learning for TensorFlow and others. Okay, you can select this and go through this process of launching an EC2 instance. Now, I'll not go through this process because it's fairly easy to do. And once you've launched an EC2 instance, you have an IP address which you can then use to connect SSH into it. Okay, you must start to notice now that this is not an ideal developer experience, but nevertheless, you get access to an EC2 instance, and in this case, you have access to a GPU instance. I can confirm this by running NVIDIA SMI. I'll see here that I have a NVIDIA V100 GPU, right? And you can also launch a Jupyter server like I've already done here. Just pull up a Jupyter server, and you have an additional step of setting up a tunnel so that you can access your Jupyter server from your local laptop. Okay. You must notice now that this is a pretty involved workflow, right? And you can pull it up this way. So go to localhost 8888 and lab, and you have your ID. So after all this setup, you get access to this nice Jupyter client on your end where the server is running on EC2 instance, and you can let's go ahead and run this notebook. It's a simple TensorFlow notebook with just training on a Cypher10 dataset, and we can pull up NVIDIA SMI and take a look at GPU utilization as you train. Okay, so now we're going through the process of training here, and in a moment you will see here that you will see GPU utilization spike up. There you go. So the benefit of this sort of a setup is that here's your GPU utilization at around 60 or 90%. It's not a very complex model. It's a fairly simple model. But the benefit of this setup, as I mentioned, is that you get access to a development environment that you're familiar with, that's hosted on AWS. You get access to up to 8 GPUs on a single EC2 instance, and also up to 16 terabytes of local storage on EBS, right? Amazon EBS. And you get access to the latest frameworks. I briefly mentioned this while choosing the AMI. Here's the documentation page for all the deep learning AMIs. You get access to a variety of deep learning AMI that's optimized for deep learning, and they're designed with support for GPUs and CPUs, x86 as well as Graviton. They come with the CUDA for GPU support, as I mentioned. And there are a range of these environments that include several different Conda environments for TensorFlow, PyTorch, and others. Okay, these and you'll also see this available here. So you have Conda environments that you can choose in order to get. So this simple yet effective setup is a great way to get started. And there are many different GPU options on EC2 instances. I'll just leave a resource here. This blog post, I go through several different GPU recommendations. Okay. All right. So a couple of tips here. The first thing is I highly recommend you use the frameworks provided by the deep learning AMI, and don't pip install or conda install deep learning frameworks from upstream, simply because the frameworks that are available upstream are not optimized with your hardware in mind. Remember, these upstream frameworks are designed to work on your laptop or on the cloud or anywhere else you're going to run it. So it doesn't have the specific optimizations of EC2. So always use the frameworks provided by DLAMI because they've been tested and optimized for CPU and GPU instances on AWS. Okay, so the challenges with this approach is that the IDE setup is complex, and it's difficult to recreate and reproduce this environment if you're going to share this with your colleague or someone else. And of course, it's not easy to scale. Of course, you can get up to 8 GPUs on a single EC2 instance, but you can't scale beyond that easily without managing networking and orchestration and all that. Okay, so what if you wanted a fully managed IDE experience? Now, there are two options on AWS here. There's a free options. Yes, you heard me right. I said free option, which is SageMaker Studio Lab IDE. And then the SageMaker Studio IDE, which is a paid option, but gives you a more complete deep learning end-to-end experience with several other capabilities that we'll talk about. Let's start with the free option that's available to you. Now, if you head over to studiolab.sagemaker.aws, you're greeted with this homepage here. You can request an account. I already have an account. Remember, this is a free option, and you log in and you get access to CPU and GPU compute resources. Both are completely free. I'm going to start up a CPU resource. And once it gets started, you get access to a hosted Jupyter Notebook interface and up to 15 GB of persistent storage. So between sessions, all your data is stored and completely available to you. And you click Open Project, and you get access to your SageMaker Studio Lab. I'll emphasize this again. This is completely free. Okay, you can get access to your own training and prototyping environment. You can train your models here. Okay, this is your personal playground, if you will, and you also have access to GPU compute resources. The GPU compute resources will give you 4 hours of training time, and the CPU will give you 12 hours of training, prototyping, and testing time. Great to learn and get started. Okay, that's Studio Lab for you. Now, the other option is SageMaker Studio IDE, which is for your production workflows. Okay, with SageMaker Studio IDE, what you get access to is let's head over to the SageMaker console. Click on SageMaker Studio. So we already saw Studio Lab here, okay, which is the free option. Now I'm going to click on Studio and launch SageMaker Studio. And I already have a studio domain set up. It's easy to go through, set up your first domain, and then launch up my Studio IDE. Okay, so what I get access to here is my Studio IDE with completely hosted, fully managed Jupyter Notebook experience here. Okay, so here are a couple of notebooks I have. We'll go through some of these examples. One of the benefits of this is you can switch compute backend very easily. Take a look at all the different compute backends that are available to you. So there's no instances to manage, there's no instances to launch. Just select the compute resources you need and switch your backend and start training. Okay, and Studio also comes with a host of other capabilities that we'll talk about, such as experiment management, monitoring your endpoints, compilation jobs. You can monitor your endpoints right here hosted. Several different capabilities that we'll talk about. So let's head back to our slide here. So you can set up your own Jupyter-based environment on EC2, or you can use one of these managed options in order to do your projects. Now, a quick tip here: use the free Studio Lab for learning and prototyping. Create an account. Takes a couple of days to get access, and then you can use it. But if you're doing anything for production, such as you need access to experiment tracking, collaboration, scaling, hosting models, use SageMaker Studio. You get end-to-end CI/CD options for MLOps. With SageMaker pipelines, you get better options with managed spot training to save cost and all that. Whole host of capabilities. Okay. Now, the benefits of this setup, of course, is that compared to the EC2 setup is you get a fully managed Jupyter-based experience, and you get access to, again, AWS optimized ML frameworks with deep learning container environment. So when using SageMaker Studio, your environment is basically a containerized environment. If you don't know what that is, hold on, I'm going to cover that. And finally, you get access to you get CPU and GPU options with Studio Lab, which is free. And with SageMaker Studio, you get a whole range of compute options, as I showed you, so that you can choose the one that's right for you if you're doing development prototyping on this instance. Okay, so so far we covered simple setups, right? How to take your deep learning to AWS and be productive with the right development experience, framework, and compute options. But often there is a need to scale. And there are a few different reasons you want to scale. You want to scale either to manage multiple experiments or to speed up your training. So let's talk about that a little bit. Now, one of the challenges with scaling or using more compute resources is that there's an assumption that your code, which is working on your development system, either your laptop or on EC2 or any specific development environment that you set up that we've discussed so far, and you take it to another environment, which is your training cluster or that you self manage or a managed cluster, and you hope that the code works. But in reality, the ML stack is pretty complex, which means you may be using a different version of framework. A different version of framework is running on the cluster there, or there's a mismatch in the GPU libraries. There's a mismatch in the driver and the operating system and so on. And this introduces multiple points of failure. Okay, and this is the biggest headache customers face with migrating machine learning code, and it's exceptionally more challenging than traditional software just because of the nature and the complexity of an ML stack, which has tighter integration with hardware, basically your CPU and GPU libraries and drivers. So one of the solutions to this is to use containers. Now, containers encapsulate not just your training code, but also all your dependencies and configuration into a simple, lightweight package that's portable and scalable. Now, containers have their roots in traditional deployments, not machine learning, but very quickly the machine learning community has adopted containers, not just for hosting models, but also for development workflows, as we'll see now. They give you this portable development environment that you can share with others and hope to reproduce results regardless of where you're running it. Now, if you're a seasoned deep learning practitioner who's probably new to containers, a question you may have is like, hey, I use Conda environments. I already make sure that my environment is portable and reproducible. But remember that Conda environments only encapsulate your code and your frameworks and at most Python versions, but they don't really encapsulate your CPU libraries optimized for hardware such as your MKL and others, your GPU libraries, which include your cuDNN and cuBLAS and various other GPU libraries that deep learning frameworks use, and also drivers, and also don't encapsulate the OS and OS kernel and all that. Okay. Containers, on the other hand, not just encapsulate your code, framework, and dependencies in Python, but will also encapsulate your CPU libraries, your GPU libraries, and drivers can also be containerized into their own dedicated container driver containers, so that what you get is an even more portable way of sharing and reproducing results that is not possible with Python environments or other mechanisms. There are virtual machines, but they're too big and too cumbersome to share, like sharing an entire AMI. They're too big and too cumbersome. They're not lightweight, they're not portable. And containers strike this nice little balance between portability and lightweightness for your machine learning environments, which is why they've become so popular for machine learning workflows. Okay, so that's a summary of why you would want to use containers. Now, oftentimes, as a deep learning practitioner, you don't want to deal with infrastructure and containers, and I completely empathize with you. I don't want to deal with containers either, which is why a lot of these optimized containers are readily available to you. AWS makes them available on Elastic Container Registry, which is where container images are hosted. Now, if you head over to this link, you should see a big list of containers options here. Now, there are several different containers. Let's take a look at some container images in this repository under available images. So you'll see container images available for let's say TensorFlow. Let's go to TensorFlow here and see a list of TensorFlow containers. So there's PyTorch containers, TensorFlow containers for CPUs and GPUs, and optimized for distributed training with Harvard, yes or no, for training and for inference and for different regions. Okay, these are again optimized frameworks that you should be using rather than using upstream frameworks, because these are optimized and tested for AWS hardware. Okay, I highly encourage you to use this instead of using your own. If you want to customize a container, or by all means, just pull one of these container images and customize it if you have the experience to do that. Or you can start with one of these container images. Now you're probably wondering, okay, there's a container image, but I don't know how to use it, right? Fair enough. That's a good point. So we'll discuss how you can take advantage of this, leverage these for your workflows. Okay. Heading back to our slide here. One of the benefits of having everything integrated is that you get better performance. By integrated, I mean having the compute layer, which is your CPUs and GPUs and hardware, storage options, all the networking and frameworks that you're going to use with containers working together. And one of the services that enable you to do that is Amazon SageMaker, because with SageMaker, you get a fully managed infrastructure and training service, which way you just bring in your training scripts depending on whichever framework you're working with, and it enables you to scale, and you're ensure that you're getting the best performance of your compute resources on AWS. So there are a couple of reasons to scale. Okay, why I keep talking about scaling. Everyone keeps talking about scaling deep learning, right? And oftentimes you may be wondering, I don't have a need to scale. Why do I need to scale? So one of the reasons why you want to scale is to run multiple experiments. Now, many of these experiments could be finding the best hyperparameter, or finding the best model architecture, or maybe simply training on different data sets. And you have to go through many different experiment steps. And these are all embarrassingly parallel, which means you can run all of these on different compute instances. Now, if you were to run it on the same instance in a loop versus running them in parallel on multiple instances, the cost to you would be the same, simply because you're using the same resources, but in parallel versus in a sequential manner, right? So there's a need to scale out experiments so that you can get faster results. But as a deep learning practitioner, I understand you may not have the infrastructure experience to manage a cluster like this, which is where SageMaker fills in that gap, and we'll take a look at an example. Okay, so let's head to our code example here. So back into my SageMaker studio. So one of the best ways to take a look at um, our experiment management is, let me open up an example here. Here's a Jupyter notebook where I have an example of running a parallel experiment job in multiple jobs, and taking a look at results to find the best combination of hyperparameters. Now, this example is based on this blog post that I have here, which will be linked to you, and I'll share this to you at the end of the presentation. So the example here goes through the process of creating an experiment, and an experiment is something that you want to achieve. You want to decide if a custom model architecture delivers better results than, say, ResNet or VGG or something like that. So you can define what it is. So you can create an experiment in SageMaker, and then you can specify a combination of parameters that you want to run in parallel. So maybe you want to run ResNet and custom architecture with different optimizers and different number of epochs and all that, right? You can enumerate these, and in SageMaker you can create an experiment, and you can loop through it and run through all these different combinations. The benefit is that SageMaker will run all of these in parallel. So each of these experiment trials will consume one GPU, one instance, and they're going to run in parallel. Okay, they're going to run in parallel. And at the end of it, you can take a summary look at all the different results. Now, after running all of these, I can sort by test accuracy and decide which gave me, like, the best was my custom model architecture with Adam optimizer ran for 120 epochs, versus the worst was my custom architecture with SGD, right here at the bottom. Okay, So the benefit is that now I ran all of these in parallel, and I can take a look at the results. And I notice I never needed to set up. I never needed to set up my infrastructure. So all the magic happens here at the SageMaker estimator function, where I simply loop through running multiple of these, and these are fully managed as an experiment. Now, SageMaker Studio gives you access to managing these experiments right here within the Jupyter interface. So you can go open this up and take a look at all the training jobs that we ran here. These are all dedicated training jobs that ran to run your experiments. Okay, so this is a simple example, even if you're not distributed training, to take advantage of multiple resources. Now, the second reason you want to scale your deep learning projects on AWS in a simple way is to get faster results. And how do you get faster results? There are two strategies. The first one is called scaling up. And simply what that means is, if you're running this on CPU instance or a smaller GPU instance, just get a bigger instance type with more compute power. And that is called scaling up. So replacing what you have with something even more powerful is called scaling up. And this will be the simplest way to do it, because this requires no code modification in most cases. You simply, if you're using a P2 instance, try a P3 instance, and if you're using P3 instance, try a P4 instance, and so on and so forth. So just try a more powerful GPU instance. The other way to speed up training is, maybe you have large data sets and you can actually scale out training. Scale out training is distributing your training across multiple instances. So you could go from tens, hundreds, or thousands of GPU accelerated instances on AWS and scale out your training to get results faster. The downside of scaling out is that you need code modifications. As we'll take a look at an example, you need to modify your training script in order to be able to scale out, just because of how scaling out distributed training works, where you need to average the gradients across these different instances. Again, the only effort on your end is to modify your code. You don't need to manage infrastructure, because SageMaker will do it for you. Now, some tips again here. Always, 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 always scale up before you decide to scale out. What I mean by that is, try to find a more powerful instance that may satisfy your time to train goals before you decide to distribute your training, because distributing training brings with it its own challenges by having to modify your hyperparameters and all that. Okay, so don't distribute training before you've tried a more powerful compute instance. And there are many, many different GPU instance types on AWS, and you can take a look at this. I have a blog post. I linked to it at the end of it. Recently updated with all the latest GPU instances. So I have key recommendations on which GPU instance to get started, with the highest performing instance to highest performing multi GPU and single instances, best bang for buck instances, best performance for cost ratio and all that. And at the very end of the blog post, I also include a summary of all the different instances that are available on AWS for you to take a look here. So I have a table with all the different capabilities. So don't jump into distributed training before you've exhausted scaling up or adding the most powerful instances. Okay, that's my pro tip for this section. Now, if you do want to do distributed training, there are a few different options. SageMaker makes it really simple for you. And the whole key idea between distributed training with distributed training is that you can take your data set, rather than process it sequentially as you do in a single instance, you can distribute it to multiple workers, but then there's a step of averaging gradients and updating all your workers, which adds some overhead. Okay. Now, so effectively you're speeding up the batch size so you can speed up the training. Now, let's take a look at an example of how this can be achieved simply on AWS. Okay. Training with a single GPU is pretty easy with SageMaker. The whole key idea behind this is, If this is your development environment, by this I mean this Jupyter environment is your development environment, then you can offload the training to a dedicated training instance rather than training here. And the whole idea is that you can decouple your development environment from your compute environment. And behind the scenes, what happens is that you will bring in your training script, and SageMaker will pull in the appropriate deep learning container, whether it's TensorFlow or PyTorch, combine them, as in load your training into this container image, spin up a cluster of 1, 2, or 100 or 1,000 GPUs you want, and start training, download the data sets from S3 automatically. So here's how it works. This is at a high level. And again, the key idea is decoupling your development environment with your training environment. So the key idea is very similar. You specify your hyperparameters and you set up an estimator function. Now, there are a few important things here. You'll specify that you want a GPU instance, you want only one of it. You can specify your TensorFlow framework version if you want, and then your Python version. And then you call the fit function to start training. Now, all you need to do is bring in your training script here, which is, in my case, Cypher 10 TF2. And let's go take a look at what this looks like. So in my code example here, and this is your very simple TensorFlow training script, nothing fancy here. We're processing our data sets and then downloading our ResNet 50 model or your custom model here, and then going through the training process. Nothing fancy here. This is your straightforward training function here that you would run locally, but you'll add some parameter parsing, which tells SageMaker that it can pass your hyperparameters as command line arguments so that it can train on these. Okay, so after you do that training, you call the estimator fit function, and SageMaker will spin up this instance for you automatically and go through the process of training on that instance. And at the end, it'll give you training seconds and billable seconds. The benefit of this is, of course, you don't need to constantly keep running a GPU instance in order to train. You can run your development on just a CPU backend, like as I'm doing here. I'm just running this on a CPU development environment. It costs less, and then I can still train on a GPU instance because my development environment is decoupled with my training environment. And of course, I can take a look at my test results too with my test accuracy and all that. So yeah, that is training on a single GPU. So what does it take to scale to distributed training? Almost no code changes as far as running with SageMaker is concerned. Some code changes to your training script. Okay, so the only code change you will make to the estimator function is you'll add a new distributions parameters. So you'll call it SageMaker distributed data parallel mode enabled true. Okay, this is important because you're telling SageMaker that it needs to launch multiple instances, and instance count here is, in our case, one instance count, but it has 8 GPUs, 8 NVIDIA V100. So you want it distributed across 8 GPUs. Now this could be 16 or 32, whatever you want, right? And the code is a slightly different code because it requires modifications. So the rest of this script is plain, estimator function and fit, but you need to modify your training script in order to be able to take advantage of distributed. And this, you would have to do this no matter what, no matter which approach you're using to distribute training. The infrastructure is managed by SageMaker, but you have to make modifications to your training script. So the few modifications include communicating the size of the cluster, in this case 8 GPUs, and then you'll want to make some updates to I'm using gradient tape here. You need to wrap the gradient tape with the distributed gradient tape API that's provided to you by SageMaker distributed, and a few other changes to broadcast the variables, the gradients, so that you can do an all reduce operation, and the all reduce operation is here. Again, most people don't need this. I don't expect you to be using distributed training. Most people don't need this, but if you do, I have a blog post where I spend more time explaining how this works. Again, my tip for the day is always scale up. Um, Always scale up before you scale out, because scaling out is more complicated and it introduces more opportunities for errors. Okay, so another question we commonly get with deep learning projects on AWS is like, what are the best storage options? If you're moderate to large data sets, I highly recommend using Amazon S3, because with SageMaker, SageMaker will automatically copy your data sets from S3 to the training cluster. And if your data set is large, it can also stream your data set from S3 to the training instance where you're running the training. Now, if you have data sets in a shared file system like Amazon EFS that's perhaps being shared with other applications or other use cases, then you can also use mount such a file system to the training cluster so that the data set is accessible to all the training instances, whether it's one or multiple. And finally, if you really want the best performing state-of-the-art file system, then FSX cluster is also supported, which behaves like a file system, but it's also natively integrated with Amazon S3, which means you get the benefits of a file system access, but also backed up into Amazon S3. So these are your options, but S3 will satisfy most deep learning use case needs. Okay, so we've covered different different development environment approaches, free as well as fully managed and DIY with EC2. We covered scaling for experimentation as well as distributed training, and how to simplify that with Amazon SageMaker. Now let's take a look at model hosting and deployment. And this is often a challenge for developers, for data scientists specifically, because they don't want to deal with hosted models, and SageMaker really simplifies that with a couple of clicks. And the benefit of that is that you don't need to rely on an infrastructure expert to do this. You can manage it yourself. And let's take a look at a few different options. So there are several different deployment options. The two we'll discuss today is SageMaker real-time inference, wherein you have a dedicated instance that you can use to serve inference requests, such as a CPU instance or a GPU instance. But the more exciting one, in my opinion, is SageMaker serverless inference, wherein you don't need to manage infrastructure at all. It's based on invocation, so you'll only be charged based on invocations. You don't need to manage the instance type, especially if you have sporadic requests coming in through the day. Then this is the best option. It recently became generally available, and we'll go through a demo of this. There are a few other options, such as asynchronous inference, where you can requests are queued. If you have multiple requests coming in throughout the day, you can have it queued and processed asynchronously, which way you are not waiting for a real-time response or even a delayed real-time response. You basically don't care about the response time. You can save some cost by doing asynchronous inference. And finally, there's batch transform if you're doing offline processing of large batches of data. So we'll take an example of the real-time and serverless option here. Okay, and let's go to our code example again. I'm going through a lot of demos, but I'm going to be sharing all of these with you. These are all available on my GitHub. I'll share a link with you at the end of the talk. And let's go through the high-level overview of how deployment works on AWS and share a code example with you. Okay, at a very high level, deployment involves 3 steps. So once you finish training your model on SageMaker, whether it's locally on an EC2 instance, on SageMaker Studio Lab or SageMaker Studio, or on distributed training with SageMaker training, whatever it is, you create a trained model. Now this model needs to be registered. So you need to create a model using a create model API. And in this, you'll specify what kind of serving container you need. If it's a TensorFlow model, then you'll use TensorFlow serving. If it's PyTorch, you can use TorchServe. There are also other serving containers such as NVIDIA's Triton server, So you have several different options. And in the code example, I'll go through this. After you create a model, you'll create an endpoint configuration. And this is where you'll specify if you want a serverless endpoint or you want a real-time endpoint. As I mentioned, serverless is when you have sporadic requests. Serverless, you don't have to manage resources. It'll automatically do this for you. With real time, you have to specify the instance type. You want a CPU or a GPU, and so on and so forth. And then you can create an endpoint. It's 3 steps. Okay. Now, I go through a lot of this in this video that's linked here that I'll share with you. But essentially, I will go through a brief overview of what this looks like in this image here. So with serverless inference, as I mentioned, if you're say a retailer, you get traffic on specific times in the day. For example, in the mornings and in the evenings, but you have no traffic during the middle of the day, right? So having an EC2 instance or a instance continuously running will cost you, the cost per inference will be higher simply because it's running all the time. Whereas if you have this kind of sporadic intermittent requests, it's better to have a serverless inference model where you're only charged per invocation and not for the duration of the instance running. The downside of this is, of course, you don't get to choose the compute type. And if the endpoint has been idle for a while, there's a cold start period. So there's a cold start period that will come into picture if it's been idle for a while. If you do have traffic that's continuous throughout the day with sufficient number of requests coming in, then it may make sense to have a dedicated instance with real-time inference. So these are your 2 options, and I go through both of these in this video in more detail. So I encourage you to check it out. So serverless for intermittent traffic, and real-time if you want that high performance, low latency performance with continuous traffic throughout the day. So let's go through this example to see how each of these options work. And remember, we'll go through the 3 steps of creating your model, creating an endpoint configuration, and then creating your endpoint. Okay. So one of the first things I'll do here is actually download a trained model. And for the purposes of demonstration, I'm just going to download a ResNet 50 model. And then I'm going to package it up and upload it into Amazon S3. Here, as you'll see here, session.upload to Amazon S3. Okay, so you can make your model available in S3, and it doesn't matter where you got the model from. It could be from your training job, or it could be something someone gave it to you. And then you want to choose your model serving container, and there are several different options in this serving container list here. You can just go search by inference for PyTorch and TensorFlow, and you can pick the one. If you don't want to pick if you don't know how to pick the right one, then just use this API here to retrieve the right framework for you. So you can specify TensorFlow, region, the version, Python, inference, and so on. And you can get access to the container image that you're going to use to host the model. And then you can create a model I'm using the Boto3 API here, and you'll specify that you want to register this model with this specific container image. And then after that, you'll create an endpoint configuration where you can specify that you need a serverless endpoint. Okay, serverless endpoints won't let you choose the compute type because they are supposed to be serverless. You don't need to manage the infrastructure, but you can specify the memory size, how much memory you need depending on the model size. Also, how many max concurrent requests it can handle. It can range from 1 to 200. And after that, you can create an endpoint. Creating an endpoint is done by using create endpoint API. And then it goes through the process of creating the endpoint, and then you can make a request. So very first time you make a request, the wall time is a little, the invocation time is a little high, because remember I mentioned that there's a cold start period. So whenever the endpoint has been idle, there's a cold start period. And once the endpoint is warm, as in it's already been executed, the next subsequent time you run, it'll be much shorter. And this is true again, subsequent requests will be quicker, and you don't get any requests for like 10 minutes for a long time, and then there's a cold start period again. Okay, and finally, you can switch from a serverless endpoint to a real-time endpoint. Let's say your traffic is going to be more predictable moving forward. Then you can switch by creating a new endpoint configuration where rather than serverless, you say it's a dedicated instance, which is a real-time instance. And then you can call an endpoint update option. It'll just update the serverless endpoint to a real-time endpoint, and then you can invoke the real point endpoint. Of course, you can choose now between CPU and GPU options and so on. Okay, so that's a quick demo of how to deploy your models without managing infrastructure on AWS. Okay, so that brings us to the end of towards the end of this webinar. Now, I want to share some resources with you. First is I have a number of blog posts here that cover how to choose the right GPUs, how to choose the right inference accelerators, how to manage experiments, how to do distributed training, debugging models, and so on. Feel free to check them out. It's on this blog here. And also all the code for today's webinar is available on this URL, Deep Learning on AWS. Feel free to check them out as well if you want to replicate some of these results. And thank you again for taking time to listen to me today. My contact information is on screen. Feel free to reach out to me using any of these channels, and I'll see you in the next Tech Talk. Thank you.